Okay, yeah, streaming is running. That's good. Okay, we're back again. The second part of lecture 11 on multibody dynamics. We ended before the coffee break with an expression of the components of the angular velocities in the body in the inertial frame as a function of the Euler angles and the time derivative of the Euler angles. And I put a dangerous band sign here because these time derivative of Euler angles are not vectors. We write them with three components but they're not vectors. Now remember, if we go to a four-dimensional world, then we would get four angular velocities, which are a vector, and then we get six time derivative of angular parameters, because we need six parameters in a four-dimensional space to describe orientation. So there you feel that this whole vector thing doesn't work. Unfortunately, in 3D, everything is three. Three angles, three axes, three planes, so it's a lot of threes in 3. Okay, back to this problem. So now we have it in the inertial frame. I would like to have it in the body fixed frame also, because then the inertia is constant, so that's also nice to have the angular velocities expressed in the body fixed frame, because of the constantness of these mass moments of inertia in the body fixed frame. Now what we could do is we can, of course, multiply with the rotation matrix this whole thing, but there's again this intuitive thing which is a lot easier, well, not really easier, but which you have to use with insight. So now the components in the body fixed frame, omega x, omega y, omega z, and sometimes we put a prime there because we use primes for xyz here and xyz here, but that's as you like it. Well, okay, so then we have to travel from this to this system, and then the first thing we encounter is this psi and the psi dot, and it's about the z-axis, and nothing changes there. So that's correct, right? Then the second hinge we encounter is this theta dot, and it's about the x-axis, so it's a theta dot, but we have to get it back into this coordinate system. So we need a transformation of r phi, but we need the backwards transformation, so we need to transpose chi of that one. So the r phi backwards. Okay, and then the last one, of course, is this hinge, and that's a rotation about the z-axis again, 0, 0, phi dot. But now we have to go twice back. We have to go through theta backwards and through psi to get in this coordinate system. So we have to get back through theta, and we have to get back through psi. Okay, if we then expand this, what do we get? Really in components and matrices, omega x prime, omega y prime, omega z prime, and on top of that I'm clear about which coordinate system. Again, we write these in the order of the angles. So again, note dangerous band, not a vector, just a bunch of time derivative of parameters. And then the matrix entries are, well, the last one is the simplest, because this guy has to do with that guy. Then this is a cosine psi, and this is a minus sine psi, and this is a 0. And then here we get a sine psi sine theta, cosine psi sine theta, of course, yeah. And then we get the cosine theta here. Okay, so that having said, we now have both expressions for the angular velocities versus the Euler angles and the time derivative of the Euler angles. Now, why am I telling you this? So that is a deep question, right? Why am I telling you all this? What is the whole purpose of this? Why do we need this? Well, then we have to get back to our equations of motion. So let's look again at our equations of motion. And I now forget about the rotational part, so I do only rotation, right? For now. Of course, to complement it, you also have to put the the Newton equation. So I'm looking at the Euler equation. So how does the Euler equation of motion look? Well, it's the sum of the torques is mass moment of inertia. I wrote a J, why I don't know, or whatever. JC, mass moment of inertia, times angular accelerations plus omega cross J omega. And of course everything expressed in some coordinate system, and I have a preference for now to do everything in the body fixed frame. Yeah, so I like to write the sum of the torques in the body fixed frame is this mass moment of inertia in the body fixed times angular acceleration in the body fixed plus omega body fixed cross I omega body fixed. Now why? Because this in the body fixed frame is constant. That's why I like that. Now what do we do with this equation? Of course, given the torques and given the state, the angular velocities, I can solve for the acceleration. So with this equation we can say, oh, omega dot in the body fixed frame is this inverse of this mass moment of inertia times minus 1, looks like a T, minus 1 times, and then the sum of the torques, of course, minus this convective term omega b cross c omega. Okay, so that's how we find our angular acceleration. And then we can integrate that, so we can say, oh, the angular speed is the angular speed at t1, angular speed at t0, right? Plus the integral from t0 to t1 of the omega dot dt. So, and we usually do this numerically, right? I have it right and done. It's a numerical integration we do. Oh, I wrote that on top of the integral sign. That's sort of nice. Numerical integration. Yeah. So numerical integration of that guy, because usually we cannot do it analytically. Okay, so that's how we update our angular velocity. Now how do we update our angles? So how do we go from, we have a set of angles, and in this case, let's say we had the Euler angles phi, theta and psi at t0. And now how do we get our phi, theta, psi at t1? That is the big question. Well, the answer is again, of course, super simple. You need the time derivatives of those guys. So if you have the time derivatives, then you can say, oh yeah, these guys, this guy and this guy at t1 is the old one, phi theta psi at t0 plus the numeric integral from t0 to t1 of phi dot theta dot psi dot dt. So that having said, I need to have what are the derivatives of the angles. So I need to know what are phi dot, theta dot, and psi dot. What are they? Well, we just recently have derived an expression, right? So the expression we derived was, it was omega is angles times phi dot. So we need this expression, but then the inverse. So let's copy it first. So this is a useful expression. Yeah, I have a lasso here. This is the one we're going to use. Yeah, duplicate. And oh, there was a little bit too much duplicate. Go back. I have to select a little bit closer. Let me try again. So, hoopla. This one, duplicate. Yeah, so, yeah, let's put that here. That's good. Zoom out again. Okay, so we have already derived, we have derived the expression the other way around. We know what the angular speed is in terms of the angle and the angular rates, but we need to have this angular rates in terms of the angular velocities, which is state times a matrix with the angle. So we have to do the inverse. Well, that is doable, right? Invert. How do we invert that? Well, phi dot theta dot psi dot equals. It's not so much, the matrix is not so big, and taking the inverse symbolically, some of you can even do it by head, I guess. I cannot, but one of the things is, if you need the inverse of a matrix, you need to first find the determinant of the matrix, and then it's 1 over the determinant. And the determinant in this case is this product, and this product. So the only one that's remaining is sine squared times sine theta minus, and then this, and then we get cosine squared phi sine theta. So we get sine phi plus cosine squared plus sine squared phi times sine theta. So we get sine theta is the determinant. So it's 1 over sine theta. That's one thing. And then we have as entries all these subdeterminants. So for this entry you have to calculate this one, for this you have to calculate this one, etc. Well, I won't go into it, and then something with a transpose. You can do it yourself. I'm just copying my result here. So sine phi cosine phi sine theta minus sine phi cosine theta cosine psi, and in the book there's also this result, right? Because I can easily make a mistake here, but I think in the book it's correct. And then 0, 0, 1, and then times, and then here we have in the B frame, at the body fixed frame, omega x, omega y, and omega z. Well, okay, and then now we have this expression, and we know what the speeds are, we know what the angles are, so we can find these time derivatives, and then we can do the numerical integration. We have updated angles, we can calculate the rotation matrix again, and we can do our calculation. However, what happens when sine theta, and is 0? When sine theta is 0, you cannot calculate this. Then it's impossible, and we call that like singular matrix, singular configuration, singular matrix, or singular configuration. So, and that's a bit strange. So already at the 0 configuration, so let's draw it. If we draw these 3 cans in series, we start with this guy, about the z-axis. Then the second one is the x-axis. So I draw everything in the 0 configuration. So this. So this is x, y, z, and this is the z prime, x prime, and this is the y prime. Now this guy, here we have apparently this theta dot, here we have apparently this phi dot, here we have the theta dot, and here we have the psi dot. So this is the configuration with those 3 angular velocities. Or if we just write it out, then according to this matrix above here, we have omega x, omega y, omega z in the B frame equals, just let's put in the numbers, theta dot, psi dot. So if everything is 0, then we only have to look at the cosine terms, and here all the sine terms result in 0, so we get 0, 1, 0, and then we get and this one is, this is 0, 0, 0. That doesn't feel good. And and then we have 1, 0, 1. Yeah, we have 3 1s, but we also have a whole row with zeros, meaning that the omega y is undetermined. Yeah, undetermined. And in other words, the omega z is just the sum of this theta dot plus psi dot. Yeah, actually it's 0 according to this. So we call this a singular configuration because with this alignment of the three axes in one plane, we can only describe angular velocity within this plane, within this zx plane. So we can only have omega in the, which plane did I say? xz plane. Because none of these axes point out into the y frame. And this is also sometimes called like gimbal lock. And it's of course very strange. It looks like, oh, this is not a good way to describe the orientation and the angular speeds, and that's correct. Of course, you will never get close to, numerically you will get close to it, not exactly in the 0 configuration. But still, you get matrices which are badly conditioned and so on. There is, of course, a trick. I mean, oh yeah, what is a gimbal? A gimbal is this thing with those, yeah, where you have all these 3 different circular things which are rotated relative to each other. It's like you put a compass in a gimbal and sometimes other instruments on a ship. I can make a quick drawing because this looks like a gimbal, because you have a thing and that rotates about the z-axis. So you have a thing here that's fixed to the ground. So that's the first circle, and then you have something which rotates about this axis. So tied to that gimbal you have these 2 rotational things, and you have this like this circle. That's the second gimbal. And then the third one is you have rotations here. And then you have here. Now I didn't follow this one, I just followed the 3 directions. But again, you can imagine if one rotates, everything rotates now, but if one rotates with respect to the other, you get the alignment, and you can get a gimbal lock. So the gimbal lock is, of course, when you go from this configuration, and this remains the same, right? And then you suddenly put them in this configuration, and then you have here these 2, and again. And then these are aligned. These which were initially not are aligned. So it's always with the middle hinge. The middle hinge determines that you get a gimbal lock. Now you can solve it. A solution is to reformulate angles. And one way would be, I take a theta star, which is a theta minus pi over 2. So if I'm very close to this configuration, right, and it's only about the middle one, this configuration, so it's about this guy, this theta. This is a singular configuration. What do? I just subtract, I go to a theta star, theta minus pi over 2, 90 degrees, meaning I change this into a system like this. This remains the same. And now I rotate that guy 90 degrees, and suddenly everything is perfectly in order, because I have 3 directions which are not, one of them is mutual. So but a disadvantage of this is non-continuity. And that conflicts with numerical integration, because in numerical integration we always assume some smoothness, smooth functions. And in this case, the theta, the thing we're now integrating, is not a smooth function. You go like this, and then ping, and you go to some other value. So there are jumps. And if you then want to do numerical integration, then the tangents are discontinuous. It's like this is like a even a C0 discontinuity. So even C0, C1, C2, that everything is discontinuous, and that's bad. Then you have to restart actually the whole numerical integration. Restart numerical integration. You cannot rely on the past. You cannot use that. So that is a very bad way actually to work with. So this gimbal lock will always happen, whatever you do. I mean, you would say, oh, I start with a X, Y, and Z axis, but then there was always a time when the middle one makes it such that two of them are aligned. And then you can say, no, I do crooked axis. I do one like this, and a crooked X like that, and a third like that. But there is always some rotation about the middle one, which finally will get two of them in a plane, and everything is in a plane, some plane. And then again you have gimbal lock. So gimbal lock is everywhere within these three Euler angles. And you would think, well, this is unsolvable. Well, there was one smart guy who found a solution. And I now want to talk about Euler's theorem on 3D rotation. Of course, it was Euler who solved the problem. Now, it's a bit funny because he created the problem, right, with his three Euler angles, and then he thought, oh, nice problem, I can solve that. Sort of self-fulfilling thing, but no, I'm joking. So, Euler theorem on what is the theorem? Any rotation in 3D can be described by a rotation about a fixed axis at a given angle. So what does he say? He say, well, if I have some object here, and my coordinate system is x, y, z, and this also has some local coordinate system, and take any configuration, like this configuration. How did I get there? Well, I can calculate an axis and an angle which made this go into this. There's one unique axis and angle to get it there. Well, you don't forget the word unique. There's one set of axis angle which got it there. So you start here, you get there. How do you get there? Well, there's one axis and one rotation to get there. There's also the opposite one, the opposite angle. So it's not just that unique, but there is an axis and an angle to get there. And that is the whole way how he solves this gimbal lock problem. He says, okay, let's make a drawing. Let's say we have here a coordinate system, x, y, and z. And then we have an axis of rotation, right? That's here. And that we call this the axis of rotation. Axis of rotation, I just pick one. And the head means that the length of this vector is 1. That's a unit vector. And unit vector. And then we're going to rotate about an angle theta. So let's say we start with the point P here and we go here. So we start here. Oh, that's not good. So we start with the vector here. And I call that P prime. That's how we start. And then we go to this position. And that is P. It's of course the same point, but this is vector P prime becoming vector P in the inertial frame here. And then clearly this is the angle of rotation, right? So this is mu, and that is the angle of rotation. So you can imagine any rotation in space can be formed in this way. Just take an axis and do a certain turn about it with mu, and then all the points move. Of course, all the points on the axis don't change, eh? But all the other points then they change. Now, for these parameters, for the axis and the angle, we want to derive what is the rotation matrix. How does it go? So, what is the rotation matrix? That's the question. In terms of this n, this axis, and this angle mu, right? Now we're going to look along the rotational axis. So we do a top view. Gonna look, and now we have to draw a circle. So if we do a top view of that guy, then we that's not a nice circle. We get a circle. Circle has a center, of course. Okay, and then we start from P prime to P. Well, it doesn't matter where you start, but let's say we start here. So apparently this is P prime. We have a top view. So this is then this line in projection is then P prime. And then in projection, point P is here. Of course, this is the angle, mu, right? And let's elongate a little bit. So this is the angle mu. And now let's put a dot here to indicate this is this vector, right? And then the whole thing is how do we get from P prime to P? And because that is our transformation, and then we know what our rotation matrix is. Well, first I'm going to build some base vectors. I'm going to build base vectors. And the first two base vectors, A and B. And this will be my A base vector. B, oh, this was the B. This was the B, and apparently this is the A. To like this orthogonal base which we built. Now, how do we build them? Well, the A vector is a vector. The A, this one, is perpendicular to the axis, right? So this one is perpendicular to this axis, and it's perpendicular to this vector. So if we just take a cross product, and then we have to do the order right. So if we do n cross p prime, yeah, we get A. And the length is exactly right. The length is length of this guy and the length of that guy, so that's exactly here at the end of the circle. Likewise, we can also build B. Now when we have A and we have n, we can build B. And that's A cross n hat. So we now build this, and then of course we want to substitute it here, so we get B is n hat cross p prime cross n hat. And then the question, the rotation matrix, is how do we get from p prime to p? That is the thing. And using our A and our B and our angle mu. Using the two base vectors here and the angle. Okay, let's start. So P is, well, we start, to get here, we start here. This is our starting point, P prime. P prime. Then I have to walk in the direction of B and in the direction of A to get there, but I cannot take the whole direction of B and the whole direction of A. I have to walk backwards with B, and B was called n hat cross p prime cross n hat. Yeah. Oh, well, maybe it's better to first say that's B. So backwards over B, and how long? Well, if this is mu, then I have to walk back this short distance and then go up. Now this short distance back is 1 minus cosine mu, right? That's this, times this B vector. And then I have to go up, plus, but not all the way, only sine mu times A. Then we're going to substitute these expressions, right? So we get P prime minus 1 minus cosine mu times B is n hat cross p prime cross n hat, yeah, plus then we get sine mu times an a was called n hat cross p prime. Okay, we're almost there. Actually, I want to have all the p primes at the end, so I'm going to change the order of the cross product, and if I change the order of this guy, I have to change the sign, so I get p prime plus 1 minus cosine mu. I get n hat cross p prime, yeah, plus sine phi n hat cross p prime. Okie dokie. Now we're almost there. So now in the first part of the lecture we learned how to write cross products as by matrix multiplications. So that's what we're going to do. So we're going to use a tilde notation for this n vector. We're going to make a matrix out of that. And secondly, I'm going to change the sine mu and cosine mu to half angle. And you will see in a minute why I'm going to do that. So it's going to say use half angles for cosine mu and sine mu. And what do we mean by that? Well, we have we have these expressions like the sine of 2 alpha, remember, is a 2 sine alpha cosine alpha. So what we're going to do, of course, is we're going to say the sine of mu is 2 times the sine of mu over 2 times cosine mu over 2. That's what we're going to use. And now 1 minus cosine mu, how we're going to do that? Well, we know cosine 2 alpha is cosine squared, yeah, alpha minus sine squared alpha. That's what I remember. And of course that we can write as with the cosine squared and the sine squared as 1 minus 2 sine squared alpha, yeah. And then we can recast it, because here we have a cosine and here we have a 1. So finally we can then write that 2 times sine squared alpha is 1 minus cosine 2 alpha. So what we're going to use in our thing is, of course, 1 minus cosine mu is 2 times sine mu over 2 sine mu over 2. So those two things we're now going to substitute in here. Yeah. And then finally, what do we get? We get p is p prime plus 2 times, and then I write sine mu over 2 sine mu over 2, just a shorthand notation for that. And then we get this n cross product with n cross product with p prime plus, and then we get here, now we do the 2 sine mu over 2 cosine mu over 2 n hat cross p prime. Now Euler defines the following parameters. Define the Euler parameters as, I start with one parameter, a scalar, and that's the cosine of mu over 2. Here we see this cosine mu over 2. For the rest that's nowhere, that's the only place. And then I'm going to define a vector delta, lambda, and it has 3 components, lambda 1, lambda 2, lambda 3, Euler parameters, and they are the sine of mu over 2 times this nx, ny, nz. This non-vector. So, and why do I do that? Well, I see here an n and a sine mu over 2, and I see here 2 times an n and 2 times a sine over 2. So with these 4 parameters, I can now describe this expression. Yeah, so let's do that. So then we get p is p prime plus 2 times the lambda times cross product with lambda cross p prime plus 2 times lambda 0. Remind, there's this scalar here. And then we have the lambda cross product with p prime. Now we're going to use, of course, this tilde notation in such a way that if we say lambda cross product with x, we're going to write as a lambda tilde times x, where the lambda tilde is this matrix 0, 0, 0, lambda 1 minus lambda 1, lambda 2 minus lambda 2, lambda 3 minus lambda 3, this tilde matrix. If we then do that, then we can write everything, this expression, we get rid of all the cross products and we can write it as a matrix vector expression. So we get P is P prime plus 2 times lambda tilde times this P prime plus 2 times lambda 0 lambda tilde times this P prime. And since it's now a nice matrix vector expression, right? It's all matrix vectors. Now we can pull out this whole P prime nicely and we can say, oh, P is apparently the identity matrix for this P prime plus 2 times this strange double product of the tilde matrices plus 2 lambda 0 lambda tilde P prime. And the conclusion is, of course, that this must be the rotation matrix, because then we have, this is the rotation matrix in terms of lambda times P prime. Or ergo, this rotation matrix in terms of these Euler parameters is given by this identity plus 2 times tilde plus 2 times lambda 0 lambda tilde. A few words. Why is this beneficial? Well, first of all, R is bilinear in the lambdas. So you have no sine or cosine to calculate. If you take the first derivative of this with respect to lambda, you get linear in lambda, and if you take the second derivative of this one, you get just constants. So it's very simple. Now, how does it look like? Well, this, if we expand this double product of these lambdas, it looks something like this: lambda 2 squared minus lambda 3 squared. This is lambda 3 squared minus lambda 1 squared, and this is minus lambda 1 squared minus lambda 2 squared. Here we get lambda 1, lambda 2, lambda 1, lambda 3, lambda 2, lambda 1, lambda 2, lambda 3, and you might think, why can I do that so quickly? I'm not looking at my paper, because it's very systematic. Lambda 3, lambda 1, lambda 3, lambda 2. And this looks, of course, a lot like a mass moment of inertias, right? Where you had about the x-axis is y squared plus z squared, etc., etc. And of course, there is also this double cross product in there. So looks a lot like the integral of y squared plus z squared dm is what was it, y xx, etc. And also these off-diagonal terms. Anyway, if you expand this, as I said, it's bilinear in the lambdas. Yeah, I'm tempted just to write this matrix just to show you how it looks. We still have 5 minutes, so it starts with lambda 0 squared, then plus lambda 1 squared minus lambda 2 squared minus lambda 3 squared. Then the second diagonal is lambda 0 squared minus lambda 1 squared plus lambda 2 squared minus lambda 3 squared. And you see again that it's very systematic here too. Let's pull this one a little bit aside, yeah. And then the last one, it's lambda 0 squared plus lambda 1 squared plus lambda 2 squared minus lambda 3 squared. Then here on the off-diagonal terms we get lambda 1, lambda 2 minus lambda 0, lambda 3, and here I get 2 times lambda 1, lambda 2 plus lambda 0, lambda 3. And note, the whole thing is not asymmetric. Part of it is asymmetric, which has to do, of course, with this guy. Lambda 0 times this one, as you see. And the other one is a symmetric part that comes from this part. That's the symmetric part here. Likewise, we get a 2 here, lambda 1, lambda 3, right? Yeah, plus lambda 1. Yeah, lambda 2, because that's from the cross product, and here we get the negative 1, lambda 3, minus lambda 0, lambda 2, and the last one, etc. Well, look in the book, you can think it up. And what is the disadvantage? Well, finally, of course, we have to write down what the expressions are for the angular speeds, right? And if we do that, then it turns out that we have no singularities. Now, there's of course one problem. We have 4 parameters, and we only need 3. Remember? Euler's theorem was you can describe a rotational matrix with 3 parameters. So why 4? And what is the dependency? What is the dependency or constraint dependency in these four parameters? Well, the dependency is super simple, of course. If you look at them, if you look at the definition, like lambda 0 was defined as cosine mu over 2, and lambda 1 was defined as sine mu over 2 times this unit vector, then if I take the sum of the squares of these guys, what do I get? I get cosine squared mu over 2 plus sine squared mu over 2, or in other words I get 1. Or in other words, the sum of the squares of this guy, so lambda I is 1. That is the constraint we have. So that is the constraint on the Euler parameters. Now you would think, oh, that is a disadvantage having these constraints, and indeed in the old days, in the days of Euler, they were not so invoked. They were not used, the Euler parameters. However, we with our computers and our differential algebraic equation approach, we can easily deal with constraints. So we have no problem to have more coordinates. We just add constraints and we then project them, and then we can just calculate along. The big benefit of these Euler parameters is that the rotation matrix is a quadratic simple thing in the lambdas, plus the expressions, as you will see in the book. Time does not permit to show here, but if you look in the book, expression from lambda, the time derivative of the lambda parameters to the angular speeds, vice versa. It's a linear transformation. It's super simple. It always exists. There is no gimbal lock problem. It's a very continuous way. So that finished the topic of today. Read the rest in chapter 19. I do homework 10, and that's for next week. And for now, yeah, and now what is the time? The time is now 15:30 until 4 o'clock. I will stay. We have a Q&A in Zoom. And if you want to know which Zoom address, then please go to Brightspace, because there you can find the link. Okay, it was my pleasure. I sign off here and I go to the Zoom.